Okay, global extrema can be a little tough for students, so I wanted to put some more review problems. These are the three I'd like to work on. In each case, we want to find the global extrema of a function. Z is a function of x and y in R3 over some region R. R is always defined in each case in the xy plane. And we want to find if they exist, because they sometimes don't always, the global max and global min, and it's okay to have ties. We've already talked about the extreme value theorem, which is an existence theorem. And so for each of these functions, they're nice polynomials, so they are continuous. And then the region, is it closed and bounded? You're looking for, does it include endpoints? Yes, greater than or equal to 0, less than or equal to 0, equal, yeah. And then is the region bounded? Is it finite? So this is a circle. Yes, you can lasso that. This region we'll see is just like a U-shaped thing in the xy plane. And this one also a quarter of a circle is what it's going to turn out to be. So yes, by the EVT, it makes sense for us to go hunt for these. And now let's take them one at a time and see what we can find. Okay, so also from a tip from the EVT or related to it is that we know where global extrema occur. There's only two types of points we have to check. And what are those? Those are your CPs and your BPs. BPs for boundary points. CPs might be within that region R, and then we'll look all around the edges of R and constrain our problem in a particular way. Okay, so we're going to do number one, and it's going to take some space. I'm going to use the whole board here for number one. Let's focus on R first and see what that region looks like. So x greater than or equal to 0, y greater than or equal to 0. And then we have this circle with a radius of 3, that's about 1.7-ish. And we're just getting the part that's in the first quadrant. So because x is greater than 0, y is greater than 0. So this is our region, R. And then what lives over or above, over or under, or possibly some of both, with the z-axis coming up from the board, is this surface. Z equals x times y squared. Well, let's think a little bit, just to, again, we don't have to know exactly what that surface looks like. We can just attack this completely algebraically and with calculus methods. But let's just try to visualize, roughly what the surface looks like. So in this part, x is positive and y is positive. And so that when you multiply a positive, clearly y squared is positive, z is going to be positive. If this is our restricted domain, then z has to be the range of this truncated surface, right? The full surface, we have no restrictions. The domain is all x, all y's. The range is minus infinity, infinity. But on this restricted, truncated surface, given this restriction, z only lives above the xy plane. So z is actually over this. Okay, and so we have some section of z that lives over this region, and we want to figure out the global extrema. We'll come back to using tech tools to really visualize what that looks like, but let's just first off handle this completely algebraically as if we knew nothing about that surface. Okay, and so we talked about CPs are good places to look for global extrema, so let's go ahead and find the CPs. CPs occur when your first partials are 0, so this is a function of x and y. So I'm going to compute f sub x and f sub y. Really easy partials to take on this first one. Partial with respect to x is y squared. Partial with respect to y is 2xy. Set both those to 0. These are places where we will have horizontal tangent planes. Clearly y is 0. Clearly x or y is 0. And we just get one CP at 0, 0. And of course, the corresponding z value would be 0 too. So if we want to write it in full point notation, we could say 0, 0, 0. Okay, that's a good place to look. And now we have to compare that CP to what happens along the boundaries. Now in this region, and for the surface that's defined over it, there will be 3 edges. There's going to be the edge defined by the x equals 0 line, y equals 0 line, and then this quarter circle given by this. So we're going to take those boundaries one at a time and see how that affects our function. And so we have the first boundary, we'll call the x equals 0 boundary. And again, geometrically, what's happening is that x equals 0, we know, is a vertical plane slicing through our surface, and we're just seeing the intersection of that vertical plane with our surface and tracing just along the intersection of those, which actually traces out something we're going to learn soon in book 3.5 called a space curve. So again, there's some surface, and then we're intersecting it with x equals 0. Another way of thinking about that, that's a trace, right? That's back to chapter 1. That's the x equals 0 trace. And so again, the intersection of that plane with the surface creates a space curve, a trace, an x equals 0 trace, and we're wondering along that trace, who's the biggest and who's the smallest. So let's go ahead and do this algebraically. X equals 0 creates, it takes our function, z is a function of x and y, given by xy squared, and it says, well, if x is 0, I'm going to plug in 0 for x, and z becomes 0. Right, so the function is really simple. It's not much to do. It's saying along that boundary, x equals 0, everything here, the z value is always 0. So actually, it is this line. It never comes up from the surface. So that this R3 surface actually is right along the line in the xy plane. Because see what happens at the y equals 0 boundary. So first boundary, second boundary, y equals 0 boundary. We take z as a function of x and y, but we're going to simplify it, forcing it to be along that boundary. And we do that by forcing y to be 0. And we plug in x times y squared, which is 0 as well. And so that means along the y equals 0 boundary, which is right here, that the surface has a z value of 0, which means it never leaves the xy plane right there. It is always in the xy plane. And so therefore, any point on this, you can call those all tied along that boundary for the global max and global min along that boundary, right? Next one, the last boundary is the x squared plus y squared equals 3 boundary. We don't need the less than, we're saying equal to because we're actually on this part of the curve right here. Okay, so let's solve for one of these variables. It doesn't matter which, but let's say we solve for y. Y will be the square root of 3 minus x squared. We only have to worry about the plus part because that's the part that's in the quadrant 1. Okay, so we can do the same thing. Z is a function of x and y, but instead of y, this is an alternative representation of y. We're forcing it, we're restricting it to live along this, which in R3 now, this is this quarter pipe coming out from the board, or once we're back in our usual orientations, sitting upright. And so we're going to intersect our surface with this quarter pipe and see the trace that comes out. So this is our first like non-linear trace. We've never seen those. We've done traces back in chapter 1 and they were always intersecting with planes. And so now we're actually intersecting with this quarter pipe. Well, algebraically, again, that's the visual of what's happening, but algebraically, you don't even need to know what that looks like. You just start cranking away on the algebra. And so our function then becomes x times y squared, which is 3 minus x squared, which is 3x minus x cubed. And that is now a function of one variable, and I can find the max or min along that boundary. So what I'm wondering is, the surface might do something like this along the boundary, and I'm wondering where is the highest and where is the smallest just along that boundary. Well, now this is this is a Calc 1 R2 problem. Z is a function of just x now, so I could say I'm going to take the derivative. If this is call this f of x, I can get the derivative, and that will be 3 minus 3x squared equals 0. X is 1. X is minus 1 are critical points. And then remember back in Calc 1, when you were finding extrema, global extrema on a function of just one variable, they happened at critical points, and where else? The other place you have to look are EPs, endpoints. So what are the endpoints along this restricted function? So right here, the endpoints happen when x is the square root of 3 and y is 0 at this point. And they happen over here when x is 0 and y is the square root of 3. So we have to add those to our values when x is 0 and when x is the square root of 3. And then we'll get the corresponding y values for each one of these x values because we're actually in this higher dimensional space. So let me start pairing these. So make some more space. When x is 1, y is 3 minus the square root of 1. So 3 minus 1 is the square root of 2. When x is minus 1, the other critical point, y is the square root of 2 as well. When x is 0, y is the square root of 3. Okay, so we have these 4 xy pairs that we need to check. Those are possible, those are our boundary points where we might have max or min along those. And we need to now check that with our CP that we found earlier. All the boundaries are always 0. So really we're just looking at this when we make our chart of all the possible places that we need to look over this region for the surface. They could happen at 0, 0, 0 was our CP. Every other boundary, x is 0, y is any y, you still get 0. On the y equals 0 boundary, you're forcing y to be 0. X can be anything at once, it doesn't matter. Z is still 0. Now on this one, this quarter pipe, x squared plus y squared equals 3 boundary. We found 4 places that we should check. So we'll have minus 1 square root of 2, 1 square root of 2, 0 square root of 3, and square root of 3, 0. So let's make some more space in our table. And we're just comparing these z values, but there's actually one thing in this table that doesn't really make sense. Which of the points in this table doesn't make sense? This when x equals minus 1, even though that was a critical point for this restricted region, you would be over here when x is minus 1 on that part, and that's not part of our region R, so we don't have to take a look at that one. So we need to evaluate 1 square root of 2 to figure out what the z value is. Go back to your original function. 1 times 2 is 2. 0 times square root of 3 our squared will be 0 and 0 there. And so we get this one value that has the max and lots of ties, infinitely many ties on any of these boundaries. The x equals 0 and y equals 0 are ties for the infinitely many global min. Anything that has x is 0, 0, or anything with any y value where x is 0, you get infinitely many mins over this region. So now I want to make sure we did all that algebraic, should be correct. Let's check that visually some of the things I was saying back here about the region and the surface over that region makes sense. We got the hunch that we did a little bit of just thinking logically about that this surface over this region should always be above the xy plane. So let's check that first, and then we'll rotate it and see if our max and min makes sense. So we'll do this with a good tool, the CalcPlot 3D tool. We're going to enter our surface first, which is xy squared. Okay, and it's got this sort of saddled nature to it. I think they might even call this like, is this a monkey tail surface or something? You imagine a monkey sitting over there, but it has a tail as well. I think that might be what this one's called. Anyway, here's our surface. That's for the entire domain, so let's restrict it now. And it's harder to do here without restriction. It's much better to just enter it as a region. So we'll turn off that surface. I'm going to enter the region that we're looking at. y goes from square root of 3 minus x squared to 0, x goes from 0 to square root of 3. Right, there's our, in purple over here, our quarter circular region, and then enter our surface, which is xy squared. We'll go from xy squared to xy squared just to that surface. Okay, so here is our surface. Let's use our arrow keys to, oh yeah, so there we go. We see the whole thing is as we suspected, always above the xy plane in this little quarter circular region. You get directly over top of it, and you start to see that purple over here. This is, again, it's kind of a skewed version of it, but you do see that that's that quarter circular. Rises up steeply. We also see along our axes, the x-axis is y equals 0 boundary, that the z value is 0. And same thing over here on the y equals, x equals 0 y-axis is the other boundary where it's also has a z value of 0 there. You can see it better from that angle. Okay, and clearly lots of ties, again, for the global min all along those boundaries. And then up here is our global max. And so we just have to figure out where is that. So it might help to rotate the surface a little bit, maybe look from over top. We were saying it was at x equals 1. So x equals 1, and y is the square root of 2. So you kind of get a, there we go, a better picture of that. It was right here is actually the tallest point once we're oriented back in the right direction. So it's a good visual check that our algebra and calculus worked correctly. Okay, so that is number 1. We had to check 3 boundaries on that one. Now let's go on to number 2. Each one of these problems has a little different point that I want to make. Okay, number 2. Again, it might help just to get a general sense of what this surface looks like over this region. So let's start with the region. Y equals x squared and y equals 4. Okay, so that would be this region. This would be the point 2, 4 right here, and minus 2, 4. Okay, now the surface may live above and below this region. And yeah, I think it might actually go below the xy plane on this one. And another good thing might be to take a look at what you think this surface generally has the shape of. The thing that jumps out at me is this x times y, and that makes a saddle surface. So that's sort of the dominant term. The plus 1 just shifts it up. And then the x and y, these linear terms, may not interact as much as near the origin. I think that this xy is sort of going to dominate that surface. Okay, but again, we don't really need to know those things, what it looks like, to algebraically solve this. A few things though, also just to make sure in your head. So there's some surface, might be above this, might dip through the board, through the whiteboard. And then there's there's 2 other surfaces. There's the y equals x squared, which we know is in back to our usual desktop orientation, is a vertical half pipe, right? Y equals 4 is a vertical plane. So there is a vertical plane, a vertical half pipe. They are intersecting our surface, creating traces. This is a y equals 4 trace. This is a nonlinear trace through the surface, but they still just create a line, a space curve on that surface. And we're wondering, when you're constraining yourself to be either on y equals 4 or y equals x squared, what is the maximum as you're tracing along that? Again, things we're going to get to very soon in book 3.5, the very beginning of that, this space curve that lives along this surface. And I'll try to make sure I remember to show you that in CalPlot 3D, those traces. Okay, all right, so now we're trying to find maximum global extrema along this restricted region. They happen at CPs and BPs. So let's get the CP first. F of xy, let's see, that'll be y minus 1 equals 0. F of y, xy will be x minus 1 equals 0. So we get a CP at x equals 1, y equals 1. And just to be complete, to get the z value, the corresponding z value would be 1 plus 1 minus 1 minus 1. So that's 0, right? Okay, so what we know is at the point 1, 1, we are on the XY plane. That's a CP. Now we need to get the BPs to compare who's the biggest and smallest out of those. And let's start with, there's really just two boundaries. Let's start with the y equals 4 boundary. When y is 4, our function f of xy becomes f of x4, and really it just becomes a function of one variable, and that will be 1 plus 4x minus x minus 4, which is 3x minus 3. Is that correct? So, okay, so then what we're saying is we're intersecting, when we intersect the y equals 4 vertical plane with our surface, we actually trace out a line. And we'll be able to check that in Calcplot 3D, see if that's true. But what about a line? Does it have critical points? No, the only thing we need to check then are endpoints. And the endpoints on the y equals 4 boundary, x goes from -2 to 2. So we should add endpoints of x equals -2, y equals 4, x equals +2, y equals 4. We need to check those when we start making our table of all the points that are of interest. Okay, let's go ahead and get that started here. So the CP for the whole problem was 1, 1, 0. We just found a couple endpoints along this boundary. This boundary didn't have any CPs to check. So the endpoints were at -2, 4, and 2, 4. And what are the corresponding z values? Let's say for x equals -2 and 4. So I'll have 1, gotta write this out. 1 -8 plus 2 minus 4. So let's see, -12 plus 3 minus 9. And then 2 and 4, put those into your function to get the corresponding z value. And I'll have 1 plus 8 minus 2 minus 4, which is 9, 3. So the z value of 3. And those are our EPs on the y equals 4 boundary. Just to remind ourselves. There's one more boundary to check, this nonlinear boundary, which happens when y equals x squared. And once again, instead of writing y, we write its representation, its alternative representation in terms of x. And now we're going to get a function of just one variable x. Z, instead of being a function of x and y, right, that's what z is now just going to be 1 plus x cubed minus x squared. So when we intersect our surface with this nonlinear half pipe, vertical half pipe, what we get is this type of function. And now this function is a function of one variable. I can ask myself what's the max and min along that trace, nonlinear trace of the function. And what I'll get is when I take a derivative, I'll get CPs, and I also have to check my EPs. The CPs happen when the derivative is 0, so I'm going to take my derivative, set it to 0, find the CPs, and then don't forget our EPs. So the EPs on y equals x squared are the same EPs. They're already in the list, no problem. So the only thing I need to add to this list are any CPs that I get. So let's see what happens when we solve this quadratic equation. Let's check if it factors. There's a chance it will because we've got these nice integers. So 3x and x, 1 and 1, and I just need to get my signs right to get the minus 2x in there. So I guess minus plus. That work, 3x squared minus 2x minus 1. Okay, so nice. We get two CPs. We get a CP at x equals, what is that, -1/3, and x equals +1. But you got to get your corresponding y values. So what happened when x was -1/3? You plug into the thing that you started restricting yourself with, which was y equals x squared. So y will be +1/9. And then when x is 1, y is 1. Okay, so I need to put those in the list because those are places along that boundary that might be max or min, and therefore places along the entire region that might be max or min. Okay, so we have, oh yeah, the 1, 1 is here, so that's actually along the boundary. There were no CPs inside this, and then we checked, we're gonna check this point, and then we're gonna add 1, 1, and let's go ahead and get the corresponding z value, so that'll be 1 plus 1 is, oh, I already have it in the list, right? I don't need it, that was the CP. So that one's already there, I just need to add this last one then, minus 1/3, positive 1/9. And then I need to plug those into my function. So I better, that'll be 1 minus 1/27 plus 1/3 minus 1/9. Let's see, should put those all over 27ths. So that'll be 27 minus 1 plus 9 minus 3. So 36 minus 4, 32, 27ths. Okay, so out of these 4 points, this was the CP on the y equals x squared boundary. So let me actually graph that up here too. Along the y equals x squared boundary, we went to x equals negative 1/3, y equals 1/9, so something about here. So it's just these 4 points that we're wondering how high or how low they are for the surface that lives above this. Okay, so we just analyze these. Clearly the min is going to be this one here, -2, 4, -9. That's our global min. Global max looks like this one at 2, 4, 3. No ties, just one each. Now let's check that with CalPlot 3D. Okay, so the region now is y goes from 0 to x squared, and x goes from -2 to 2. And then the surface changes to 1 plus x, y, minus x minus y. Did I get that right? Yeah. Wild, right? That's the section of the surface. Some is above the xy plane, some is below. Oh wait, I didn't do my, that's funny. I didn't do the, see the blue is not the shaded region that we want. We wanted to go from x squared to y equals 4, so did that really wrong. So I want to go from, the top function is 4, the bottom function is x squared. Okay, that looks better. That looks more like what we were doing. And x goes from -2 to 2. Okay, so now I have this same surface. Oh, and let's actually look at that surface separately over its entire domain. Let's turn off the region for a minute. Oops. Yeah, and turn on this surface. Oh yeah, so that was my guess earlier, was that this will have a bit of a feel of a settle surface because of the xy. If you just graph z equals xy, and then it'll, as you get further away from the origin, it might get more and more linear. The x term will take over the y term depending on where you are on that surface. Okay, so that is our surface over its entire domain, and then we're going to restrict it to just live over this purple region over here, our U-shaped region. So when we do that, we just get this section of it. And now start rotating and looking, and again, we see some of it lives above the xy plane, some below. And our calculus and analysis told us that we had a global min at x equals -2, so y equals 4. Yeah, 4 along the y. And down here we had a value of -9. So that does look correct that the z value is below the x-axis. It is right there. Again, you can kind of zoom over the top to get those points as well. where they are on the X and the Y. And then there is one max, so one min and one max, and the max is at this point here on the surface, and we have to check that we had 2 and 4, X equals positive 2, Y equals 4. So we kind of zoom it around. And let's see, I don't see that that is our 2, 4. So let me check our work on the board, make sure we've got that correct. It does look like a Z value. It actually looks like it's this point here. Negative 1/3, 1/9, 32, 27th is that peak that I'm finding. Let me check my arithmetic now on something. Stop the share. Okay, checking our work then, because there's something about the visualization that's a little off. So we got with our calculus that there should be a global max at 2, 4 with a height of Z. And it seems on the section of CalPlot 3D that it keeps kind of saying this one's the tallest. So let's go back to CalPlot 3D. And something I've noticed here, and Paul Seeberger, who's the guy that's created this, is always constantly working on it. One thing that's weird this time is that you cannot change this view. It's always from -2 to 2 for the X, -2 to 2 for the Y. And it needs to change that because we want to go up higher to 4, right? So it's only showing me part of that. This purple is only part of the region, right? My region actually extends a little bit more here. And then it's only showing me part of the surface over this partial region. I want a bigger region. And so really, like one thing you could check, one thing I did to check this, I entered a trace point, and I checked the point. When X is 2, Y is 4, where are we on this surface, or this truncated surface that's shown here? And it doesn't show up, right? Because we're beyond what it's showing me. And whereas if you enter something like 1, 2, that is on the surface at the edge of it, right? But I need to actually go to X equal 2, Y equals 4, all the way up over here. And I'm actually am much taller than what is shown here. So this is an instance where we are being visually deceived by part of the restriction of the tool over here, which usually you can lift that restriction. So maybe another way to look at it is go back to the original surface and make our surface's rectangular region a little closer to the region that we have. So X, it goes from -2 to 2, and Y, instead of going from this U-shaped thing, let's just go from 0 to 4 and make a rectangular region from 0 to 4. And when we do that and look at the surface, this is the section, again, more than we need. This is not the actual truncated surface, but it does show at X equals 2, Y equals 4, we are way up here in a much higher point than that one that was over here at like X equals 1/3, Y equals -1/9. So we do see what we expect, what the calculus shows us, and we just got a little deceived. I got stopped for a moment with the limitations of CalPlot 3D. Okay, so one more problem I want to work on, this one. A few folks asked questions like, what if my boundaries aren't, like this first problem we had a line for a boundary, another line, a curve, this one a curve, a line. What if I just have one boundary and it's a nonlinear function? So I want to work one more problem here, and then I think we've got global extrema taken care of. Okay, same problem, global extrema happen where? CPs and BPs. Let's find the CP, the BP, will the boundary, well, let's go ahead and put the region. It is square root of 8, square root of 8, it's a circle, it's everything inside there. And the boundary then is just y equals the square root of 8 minus x squared for the top half, and y equals minus the square root of 8 minus x squared for the bottom. And we're wondering, is there a CP within there? We'll see if we can find that. And then we'll also check any points on the boundary that are CPs or EPs for that particular region, just along the boundary. So let's check that interior then and see if we can get a CP that might live in the interior. So f sub x at xy, again, another nice polynomial, and generally a lot of these problems are that way just because solving these problems algebraically, you kind of need some polynomials. Real life, though, you're going to see some crazier ones. You'll see, you know, arc sines, inverse trigs, exponentials, and that's when you have to use one of these numerical methods or the tech tool. But first, we can learn the method here with this nice polynomial. F sub x is 2x plus 2y. Yeah, that's it. F sub y is 2x plus 2y. They both equal 0. Well, really, that's just the same equation, right? So this just tells us when y equals minus x, that's a CP. There's actually infinitely many CPs for this surface. Okay, well, that seems a little weird. We haven't had too many of those this term. Let's think about that. So let's think about this surface. Again, I don't need to know what it looks like, but it might help as I'm going through my algebra to stop and check very often and think, does this make sense? Well, this is exactly the same as x plus y squared, right? That's just a, yeah, foiled out, you get x squared plus 2xy plus x squared. Then what do you know about this function? This function then, again, don't worry about the restricted domain. Over this function then is always positive, right? Z is always a positive value, which means that when the z-axis comes out from the board, our surface always lives above that. It might have some similarities to paraboloids and rising quickly along the walls. We would expect that. But along the line, y equals negative x. Well, let's go ahead and graph that in here. Y equals negative x. It's staying along there. That those are CPs. Those are good places to look for local extrema for this problem. So rather than thinking about this restricted domain over the entire domain, these would be good places to look for local extrema. Well, does that make sense? Let's think about it. When y equals negative x, what happens to our function? So that's really saying this is a function of x and y. And then we're looking at function of x and negative x. Instead of putting y, put negative x. What happens? X plus negative x is 0, squared is 0. That truly is the minimum value for this function, right? Because the range for this function is all z greater than or equal to 0. So if you get a z equal to 0, that's the minimum value you could achieve. And we're saying that happens whenever you're along this line, y equals negative x. So it'd be a good idea to just go ahead and graph that function. Let's see what happens. I'm going to assume it's maybe got a bit of a half pipe feeling along the line. So let's check. So let's change this one to x plus y squared. And we'll go from -2 to -2 on both of them. Let's make a rectangular region. Okay, yeah, so this is just a piece of paper kind of folded up. Let's get a few different views as we move around. But you can see that along the line y equals x, which is right along here, that is your lowest value. Those are touching the xy plane. That's the minimum that we can achieve here for this problem. Okay, so again, we've got this thing rising up out from the board there. So CPs, we already found that this is going to be infinitely many min. And they were local min. We're going to see over this region that they're also global min because they achieve anywhere along here, including those points there, has a z-value of 0, and those are your mins. And then we now need to see where along these semicircular regions do we have max, and how many? Maybe they'll be a tie because there's some symmetry. All right, so next thing is look along the boundary. Well, there's only one boundary. The boundary is when x squared plus y squared equals 8, right? We're actually on that circle. We do as before. We take our function z as a function of x and y, and we simplify it by restricting ourselves to live on this boundary. So instead of writing y, I can write its alternative representation. Y is the square root of 8 minus x squared. But we also should think about the negative too. So I really need to think about two subproblems here. When I plug this into my function, I'm going to have, I don't know if it's easier to that one or that one. Let me think for a moment. It gets you the same place. I'm just trying to think if it'll make it a little bit easier arithmetic. I think maybe we'll plug into the first representation and see what happens. So x squared plus 2x times the square root of 8 minus x squared plus 8 minus x squared. So now that is a function of one variable. I can try to find the maximum of that, which happen at CPs and EPs. In this case, the EPs, x will range from minus square root of 8 to square root of 8 when I'm looking at the top half of the circle, and same thing when I'm looking at the bottom half of the circle. So the EPs I would need to check. So x, y, z. I need to put in minus or positive square root of 8, this point here, and y is then 0, and then I'll do on the other side this point, negative square root of 8, 0, and plug those into our function. It might be easier to plug in here, so that'll be 8 and 8. But now I need to also get CPs, so I'll come back to the second half of the function. Leave a little space. We need to take our derivative now of this one function of one variable. And let's see, oh, these go away. The 8, when I take its derivative, goes away. So I just need to focus on this, which is a product rule. First times derivative of the second. So let me write that in its exponent form. So times the power down a power times the derivative of what's inside, minus 2x. 1/2 and 2 go away. So I'll have a minus 2x squared divided by square root of 8 minus x squared. That's the derivative. I want to set it to 0 to get critical points. Do I have everything in that one right? And we see x equals 0. And then that means y would be square root of 8. And the z would be 8. And if we looked at the second subproblem, we'd see by symmetry we would get the other point. So these are the 4 points on the circle. 0 or negative square root of 8, which also gives us a z value of 8. And okay. Oh, I forgot the second half of the product rule. Yeah, that's what I've done. Let's take these out for a minute. I just did the first half of the product rule. First times derivative of the second, plus second times derivative of the first. Okay. Set that to 0. Okay, a little bit more algebra. We're gonna need some room. I'm still gonna get that, what I had, negative 2x squared square root of 8 minus x squared plus 2 square root 8 minus x squared equals 0. Okay, a little messier, but I think this is still doable with algebra. We don't need to use a numerical tool. We'll bring that to the other side. So 2 square root of 8 minus x squared equals 2x squared square root of 8 minus x squared. Cross multiply. 2 times 8 minus x squared equals 2x squared. 16 minus 2x squared equals 2x squared. 16 equals 4x squared. X is 2, x is minus 2. And get their corresponding y values. When x is 2, y is what? Well, it came from being on this boundary. When x is 2, y must be 2. And same thing, when x is minus 2, y must be 2 or negative 2, right? So I've got some more points to put in here. I can put 2, 2, 2, negative 2, negative 2, 2, negative 2, negative 2. And I need to check all their z values. All right, so let's see. When I plug 2, 2, 4 is 8, plus another 8 is 16. And yet, 2 and actually it's easier plugging here. 2 and negative 2 will give me 0. Negative 2 and 2 is 0. Negative 2 is 4. Negative 4 squared is 16. Okay, so I get several points in my list to check. I have, and don't forget our CP, which was when we have x and negative x, we get 0. Okay, so of these points, the biggest one, let's use a different color, maybe red, is here. And here we have a tie. 2, 2 would be like this point, and negative 2, this point. Those are our global max. And then anything along the line y equals negative x, of which these 2 points also follow that rule. Those are our global mins. So anything along here are our global mins. All right, so let's check that visually. Okay, there was our surface, but not restricted to our region. So let's see. Let's do a region. Turn this surface off. Our region, y goes from the square root of 8 minus x squared to the negative of that. And x goes from negative square root of 8 to the positive square root of 8. And then the surface is x plus y squared to itself. And you have to hit enter or it'll show the one I previously had in there. Okay, there is our, oh wait, our rectangular region doesn't look right. Oh, it's probably because of the, oh yeah, because it's stuck again. I don't know how to change this. The two and the region here that's shown, or the view window in this area is from -2 to 2, and we need it. Oh, let me see if I can. This might. Oh, there we go. That's all I had to do before. Okay, that does now show us the boundary is the circle, and then the region is everything within that. Again, you can move this around and it shows the different z values in the top in the green. And we were claiming that anything along roughly this line will have a value of 0. And again, I run along that and watching those z values of 0. Those are your mins, infinitely many. And then the max we said was at 2, 2 over here, with a z value of 16, and you can kind of make it get pretty close. You can put it in exactly if you did it over here. 2, 2, and there we are. It's but I'd have to zoom out on this surface and see again that there is symmetry, that there are 2 points. There's the one at the peak, and then the other one would be over here at x equals -2, y equals -2, and it finds that. Okay, make sure there's any other comments on these practice problems. I think that covers it. If I think of more, I'll make another video, another short review video. I think that should also help you visualize what's actually happening when you're doing it. I think that's a great help here. Do these pictures and try to get a general sense of what the surface looks like rather than just cranking away with the algebra. All right, have fun. I remember the other thing I wanted to show you. So calc plot 3D. Okay, so here is our surface again. X plus y squared for that third example. Rotate it again. I got this like taco shell basically, and it would extend up. Right, it'll just keep those walls keep climbing, and then the region R, which is the boundary of it is a circle with a radius of square root of 8. That actually, though, x squared plus y squared equals 8, you can think about that in R3 as a surface. And so I entered an implicit surface. So I selected implicit surface and entered this equation here, which gives us z is free. So it clearly takes that circle and extends it up and makes a cylinder. And that's a cylinder shown here. And it'll go like on this x squared plus y squared equals 8. We already found that like at -2, -2, the function z equals x plus y all squared. -2 plus -2 is -4 squared is 16. So we have a z value of 16. So that's why I entered this cylinder. Just went all the way up to 16 on the z value to show the cylinder. For some reason, I can't get it to show the surface actually goes all the way up this taco-shaped surface. We'll come up and meet up here at 16. Now, what I was trying to show, talk about earlier, was that, again, the intersection of the cylinder and our surface, there's looking at over the top, you see the surface down in there in the bottom. That's half pipe. Come around. When you intersect these, they create a trace. The intersection of these two surfaces actually creates a trace that is a nonlinear trace that actually turns out to be a space curve. Now, you don't know this next part I'm going to show you. So I entered this space curve, selected send space curve. You will learn that. That's chapter 1 of book 3.5, so a couple weeks. Again, you don't know how I got these equations, but when I turn this on, make it in red. Let's see. So here it is. There is that space curve, which is the intersection of these two surfaces. And when I come around, okay, there it is a little bit. Seeing the red, it comes up. And in fact, if I remove both surfaces and I'm just left with the space curve, again, it would actually trace out symmetry over here. I need to adjust some values on the space curve here, but that red is the intersection of those two surfaces, and you're really just asking along this one-dimensional line in three-dimensional space, what is the max and min? And you're doing that, again, all the work we did here is just saying, if I'm restricted, I'm constrained, I have this three-dimensional surface, but I'm constraining it to live on this boundary, then the global extrema along that are really just the extrema along this space curve. Again, stuff that's coming soon, but we're thinking about it in a couple different ways. But that isn't the only place, again, that global extrema would occur. You have to make sure you check in the interior, and the only place it can happen in the interior is at CPs, which are your local extrema. So that's how the local and the global kind of comes together. The local extrema, those give you your CPs, which are good places that might be global extrema, and then the global extrema, you have to make sure you check your boundaries, and that is another way of thinking about the boundary is really creating constrained optimization. You're constraining that surface to live on that boundary, which really creates this space curve. Okay, hope that visual helps.